If you take a step back and look at the universe, not from the perspective of a single object, but as a whole dynamic system, one thing becomes immediately obvious. Almost everything is spinning. Planets twirl, stars rotate, galaxies whirl in enormous spirals. Black holes spin so fast that their surfaces blur the line between space and time. And even subatomic particles are said to possess spin, although in their case it means something very different than physical rotation. The universe is not a quiet, static museum of celestial statues. It's a cosmic dance floor, and the dancers, from the largest galaxies to the smallest bits of matter, are constantly turning. But this raises a deceptively simple question. Why? Why is spinning so universal? Why don't planets just sit there, motionless, like marbles? Why don't galaxies form into still, symmetrical blobs of stars? Why did rotation become such a dominant feature of cosmic architecture? Hi there, and welcome to Sleepy Space Traveler. I'm really glad you're here, and I hope this moment can become a gentle pause in your day. This channel was created as a quiet space for anyone who enjoys falling asleep to calm storytelling, peaceful narration, and soft explorations of science, the universe, and the mysteries around us. Here, we slow everything down. We take big ideas about space, time, reality, and existence, and turn them into simple, soothing stories you can drift off to. If this kind of content helps you relax, unwind, or fall asleep a little easier, I would really appreciate it if you could like this video and subscribe to the channel to help more people discover this space, and help us continue creating these nightly journeys. Please let me know in the comments where you're watching from and what time it is for you right now. Thank you for being here. Now, let's begin. To understand that, you have to look at one of physics's most fundamental ideas, one that feels obvious once understood but takes a while to fully appreciate: angular momentum. If you've ever seen a kid spinning on a playground spinner, you've already seen angular momentum in action. Once the motion starts, it doesn't stop easily. There's no deep philosophical meaning to it. It's not about momentum in an emotional sense. It's simply a rule baked into the mathematical structure of physics that says, if something is rotating and nothing interferes, it keeps rotating. Here on Earth, we're used to things slowing down. Ice skaters eventually stop spinning. Wheels come to rest. Gyroscopes lose balance. But that's because our environment is filled with forces that sap energy: friction, air resistance, contact with surfaces. On Earth, the question isn't why things stop spinning, it's why they spin at all, given that everything is constantly being slowed down. In space, the opposite is true. There are no brakes. There is no atmosphere pulling on a galaxy. There are no asphalt roads slowing down planets. Space is, for practical purposes, frictionless. So, if something starts spinning, it keeps spinning for billions of years. Angular momentum is not just a tendency. It is a conserved quantity, which means that the universe doesn't like losing it. In the same way that energy is conserved, angular momentum is preserved unless something actively destroys it. And since the universe doesn't have many giant cosmic hands reaching in to grab things and stop them from spinning, once rotation is present, it becomes extremely persistent. But this raises another question. Who or what started everything spinning in the first place? It's not enough to say once it spins, it keeps spinning. we have to explain how stars, galaxies, and planets started rotating at all. Was there some prime cosmic twirl, like the universe being given a spin by a giant hand at the beginning of time? Not quite. Although it's a more subtle story than you might expect. The earliest moments of the universe were anything but calm. When the Big Bang happened, or more accurately, when the universe entered its hot, dense, expanding state that we call the Big Bang, matter wasn't released evenly, like fog filling an empty room. It was lumpy, uneven, chaotic. There were tiny fluctuations in density, places where matter was slightly more concentrated than average, caused by quantum randomness. Physicists sometimes call these primordial fluctuations, and they are visible today as tiny variations in the cosmic microwave background radiation. These small imperfections in density created gravitational imbalances, ripples that nudged matter into motion. If the universe had been perfectly uniform, nothing would ever have clumped into stars or galaxies. Gravity would have pulled equally from all directions, causing nothing interesting to happen. But the universe wasn't uniform, and so matter began to drift, fall, and accumulate. And when matter collapses inward under gravity, even tiny sideways motions get amplified. The process is similar to a skater pulling their arms inward. If they start with a small twist and then pull inward, they spin faster. This is conservation of angular momentum in action. The smaller you get, the faster you spin. Now, imagine an enormous cloud of gas and dark matter tens of thousands of light years wide, shrinking under its own gravity. Any tiny rotation becomes amplified immensely. What begins as an almost imperceptible swirl becomes the rotation of a galaxy. A natural question arises. Where did that initial sideways motion come from? If gravity pulls inward, what's pushing sideways? The answer goes back to those early fluctuations. Even random, tiny motions of particles, when scaled up to galactic size, create measurable angular momentum. More importantly, adjacent clumps of matter exert tidal torques on each other. Just as the moon pulls the oceans around Earth, gravitational interactions between forming protogalaxies pull on each other, twisting and stirring their shapes. Cosmological simulations show this clearly. Run a computer model of the early universe. Start with random clumps of matter, and watch how gravity shapes them. The result is startling. Spinning galaxies emerge naturally, without needing any special initial conditions or cosmic spin-starting mechanism. Rotation is not an engineered feature of the universe. It is an inevitable byproduct of gravitational collapse in a slightly imperfect environment. This explains why galaxies rotate, but stars also spin, and they spin fast. The Sun, massive as it is, rotates about once every 27 days at the equator. Young stars spin even faster, sometimes dozens of times per day, so rapidly that they're nearly torn apart by their own rotation. Why? Because stars are born from collapsing clouds of gas inside a galaxy. These clouds are already rotating because the galaxy rotates, and as they collapse, the same amplification effect occurs. Smaller radius, faster spin. Meanwhile, magnetic fields and radiation jets allow stars to shed some angular momentum, but not all of it. So, rotation remains a defining characteristic of stars throughout their lives. Planets inherit spin the same way. They form from disks of gas and dust swirling around newborn stars. This disk isn't calm. It's turbulent, chaotic, and filled with collisions. Every collision redirects angular momentum. Over millions of years, these impacts and accretion processes set the spin direction of planets. That is why most planets rotate in the same direction the star spins. But it also explains weird exceptions, such as Venus, which spins backward, and Uranus, which is tilted sideways, the cosmic scars of gargantuan collisions early in their formation. Rotation is also fundamental to black holes. When massive stars collapse, any spin they had gets compressed into a tiny region. Because angular momentum must be conserved, the resulting black hole often spins at staggering speeds, close to the speed of light at the event horizon. This spin warps space-time, powering immense jets that blast matter out into space, sometimes for millions of light years. So, at every scale, from galaxies to planets to stars to black holes, spin arises from the same physical story: collapse, torque, conservation, and amplification. But the story becomes even stranger when we go down to subatomic scales. Electrons, protons, and neutrons all have spin, but not in the sense of tiny particles physically rotating. In quantum mechanics, spin is more like an intrinsic property that affects how particles behave in magnetic fields. It's a label that tells you how the particle interacts with the universe. It is called spin, only because it behaves mathematically like angular momentum, not because electrons are literally spinning balls. Remarkably, this quantum spin plays an essential role in chemistry, magnetism, and nuclear physics. Without it, atoms would not organize into distinct shells. Molecules wouldn't form the same way, and the periodic table would look very different. You could argue that spin, quantum, or classical is responsible for the universe having interesting structure at all. A natural question arises. If objects gain spin from collapse and interactions with neighbors, could the entire universe be spinning? It sounds wild, but scientists have asked this seriously. If space-time were rotating, there would be measurable effects on the cosmic microwave background. So far, the evidence suggests that the universe as a whole is not spinning. But rotation is embedded locally in so much of its structure that the absence of global spin doesn't make it any less of a spinning universe. What makes this topic profound is not just that the universe spins, but that spin had consequences. If galaxies did not rotate, they would collapse into dense spheres. If planets didn't spin, temperatures would become extreme on each side. If stars didn't spin, magnetic fields and fusion processes would behave differently. Rotation makes the universe not just energetic, but stable and organized. Spinning systems settle, flatten into disks, and develop predictable orbits. It's ironic that something as simple as turning in circles can explain some of the most fundamental features of the cosmos. And unlike most cosmic mysteries, this one is not driven by exotic physics. It is a straightforward consequence of familiar principles, stretched across cosmic scales. The universe is spinning because nothing stopped it from spinning, because gravity inevitably generates rotation from asymmetry, and because the laws of physics ensure that once motion starts, it does not quietly fade away. The universe is a restless place. It was born with imbalance and motion, and it has been amplifying that motion ever since. When you zoom out and look at a galaxy, it is tempting to imagine it as a single unified object. rotating as if it were a rigid machine built in a factory somewhere. But a galaxy is not a thing in the mechanical sense. It is a vast community of stars, gas, dust, dark matter, and sometimes supermassive black holes, loosely held together by gravity. If you lived inside one of those stars, you wouldn't feel the galaxy spin. You wouldn't look up and see all the stars sliding by. Everything around you would feel still, because you are part of the rotation. This illustrates something subtle. Rotation is relative. A planet spinning under your feet is invisible if you're spinning with it. Galactic rotation, however, matters enormously. It determines the shape of galaxies, the formation of stars, the motion of gas clouds, and even the future survival of the galaxy itself. Spiral galaxies, the familiar pinwheel pattern you see in images from telescopes, are not shaped that way by artistic intention. They are shaped by rotation, gravity, and the way density waves move through enormous rotating disks of stars. If galaxies didn't spin, they wouldn't form spirals. They would collapse inward, become dense balls, or fragment chaotically. Rotation is a stabilizing agent on scales that are frankly ridiculous. The speeds involved are also startling. Our Milky Way rotates at hundreds of kilometers per second at the Sun's location, and faster toward the center. Yet it is also held together by gravity exerted not by visible matter, but largely by dark matter. This isn't a poetic metaphor. It's a literal gap in the accounting book. Observations show that the visible mass of galaxies isn't enough to generate the gravitational force required to keep them spinning without flying apart. Something invisible, massive, and omnipresent is holding galaxies together. This fact wasn't discovered by philosophers, it was discovered by meticulous astrophysical measurement. In the 1970s, astronomer Vera Rubin conducted observations of galactic rotation curves. Graphs showing how the velocity of stars changes with distance from the galaxy center. The results contradicted classical expectations. Instead of slowing down as distance increased, like planets in the solar system, stars at the edges of galaxies were moving just as fast, sometime faster, than stars near the center. Something was adding mass without adding light. That something is now called dark matter, and its existence is one of the most direct consequences of studying spin. Rotation exposed the universe's hidden content. Without spin, dark matter might still be invisible to us. This shows a deeper theme. Rotation, far from being a trivial property, is a revealing diagnostic tool. By measuring how fast galaxies spin, and how that speed changes with radius, we can estimate how much matter is present, and how it's distributed. Rotation curves are not just observational quirks, they are litmus tests for gravity itself. This leads to the next profound question. If galaxies continue spinning for billions of years, does that mean they eventually fly apart? Surprisingly, no. At least not because of rotation alone. A spinning system that is gravitationally bound has enough inward pull to counter the outward tendency. In the same way that Earth doesn't fling its atmosphere into space, galaxies don't fling their stars out, except when gravitational interactions disturb the system. And galaxies do disturb each other. The universe is full of encounters. Galaxies collide, merge, stretch, and pass through each other with astonishing violence. When two galaxies collide, their stars rarely smash into each other. The space between stars is just too vast. But their gravity does interact destructively. collisions scramble orbits, trigger star formation, and often alter spin direction. A merger between two galaxies transfers and redistributes angular momentum. Sometimes the result is a more organized spin. Sometimes it is chaos. For example, elliptical galaxies, the smooth, oval-shaped ones, often form from past mergers. Spirals, by contrast, seem to retain a cleaner, persistent rotation. It is no accident that ellipticals lack graceful spiral arms. Their history is one of violence that erased them. You can think of galaxy collisions as a cosmic version of car crashes involving vehicles that are made of clouds. The final wreckage isn't just bent metal, it's a completely new vehicle with different wheels, different spin, and sometimes a different driver. The universe doesn't rebuild quietly. Rotation plays a critical role inside galaxies as well. When large gas clouds begin to collapse under their own gravity, they spin faster as they shrink, just like skaters pulling their arms in. This effect flattens the cloud into a disk. Almost all stars form from disks, not spheres. And this is why planetary systems are flat. The solar system is not shaped like a snow globe. It's shaped like a pancake. Nearly everything orbits in the same plane, because it inherited the flattened structure of the disk that formed the sun. But as clean as that picture sounds, reality is messy. Star formation is extremely violent. Young stars spit out jets, flare up, and shed mass through powerful electromagnetic winds. These processes remove angular momentum, allowing stars to stabilize. If stars could not lose angular momentum, they would spin so fast during formation that they would tear themselves apart. When planets form, they undergo similar chaotic processes. Collisions with other forming bodies can alter their spin dramatically. The early solar system was filled with planet-sized objects smashing into each other. The Earth itself probably formed from a collision between two protoplanets. The Moon is thought to have formed from debris thrown off by that impact. This explains why Earth has a relatively fast rotation, and why the Moon orbits in a stable, regular way. The violence gave the Earth its day-night cycle. Without it, Earth might rotate so slowly that half the planet would bake while the other half freezes. Spin is not just a curiosity. It may have made Earth habitable. These stories repeat across the universe. Mars lost its magnetic field because its inner core cooled, ending the rotational effect that powered its dynamo. Venus rotates backward, likely due to a chaotic collision that flipped its orientation. Uranus was literally knocked on its side, becoming the cosmic equivalent of a rolling barrel. These are not exceptions. They're testimony that rotation is born in turbulence, not precision engineering. Black holes take this to a dramatic extreme. They are compact, massive, spinning objects whose rotation affects spacetime itself. A spinning black hole drags nearby space along with it in a process called frame dragging, predicted by general relativity and confirmed experimentally. If you orbit near a rotating black hole, space literally forces you to rotate as well. You cannot resist the twist. Black holes often form from collapsing stars that already have spin. When they compress, angular momentum skyrockets. Imagine trying to spin a basketball made of neutron star material. The density is so high that a rotation speed of mere thousands of revolutions per second is possible without tearing the object apart. Black holes can rotate even faster, approaching the speed of light. This rotational energy can power enormous jets of matter that shoot out for millions of light years. Some of the largest structures in the observable universe, massive radio jets, are powered by rotating black holes. Spin is not a decorative detail, it is a cosmic engine. But rotation also determines long-term fate. As galaxies evolve, they shed angular momentum through gravitational interactions, encounters, and winds. Dark matter shapes this process by providing the mass distribution that stabilizes spirals. Rotation keeps stars from collapsing inward, but too much rotation could tear things apart. The universe has found a balance between too much and too little angular momentum. That balance, oddly enough, is one reason structure exists at all. Without angular momentum, matter would collapse into tight clusters and form massive, short-lived stars. The universe might have burned itself out quickly. With too much angular momentum, matter would never collapse and stars would never form. The universe might be cold, diffuse, and lifeless. Spin is the middle ground that allows complexity. These patterns extend down to smaller scales. Electrons, protons, and neutrons have spin, even though they are not literally rotating spheres. In quantum mechanics, spin determines how a particle behaves in magnetic fields and how it can occupy energy levels in atoms. Two electrons cannot occupy the same quantum state if they have the same spin, due to the Pauli exclusion principle. This bizarre rule is responsible for the existence of chemistry. If electrons didn't have spin, atoms would collapse into featureless balls of electric charge. Matter as we know it would not exist. In other words, spin is not just everywhere. It is essential. It determines galaxies, stars, planets, magnetism, chemical bonding, and even the solidity of ordinary matter. The universe is not just spinning by coincidence. It is spinning because the laws of physics reward systems that organize angular momentum. One could ask whether spin ever stops. At cosmic scales, the answer is essentially no. Without friction or drag, rotation can persist indefinitely. A galaxy can rotate for billions or even trillions of years. Stars slow down through magnetic braking over time, but not to zero. Planets slow down due to tidal forces, but the timescales are enormous, billions of years. Earth's rotation, for instance, is gradually slowing. Millions of years ago, a day was shorter than 24 hours. Millions of years in the future, it will be longer. But these changes are so slow that no one notices. In a cosmic sense, rotation is nearly eternal. The universe is still young compared to the timescales needed to stop it. This leads to a deeper reflection. If rotation is so fundamental, what does it say about the character of the universe? The universe is not static. It is dynamic. It does not form things and leave them motionless. It sets them in motion and allows them to evolve. Rotation is not simply motion around an axis. It is a mechanism for distributing energy, organizing matter, and shaping structure. The more we study rotation, the more it reveals hidden layers of the universe. It exposes dark matter, confirms general relativity, powers black holes, drives star formation, shapes planets, enables chemistry, and defines the structure of galaxies. The universe spins because physics requires it, but also because spin is a natural consequence of imperfections and interactions. A perfectly still universe would require perfect symmetry, the kind of absolute sameness that nature almost never produces. Without slight imbalance, there is no collapse. Without collapse, no amplification. Without amplification, no galaxies, no stars, no planets, no atoms with structure. In a strange way, rotation is the universe's response to imperfection. It takes small asymmetries and turns them into coherent motion, and the result is a cosmos full of swirling patterns, from the graceful arms of galaxies to the tiny quantum rotations that allow atoms to exist. The universe we live in is not a static monument. It is a restless organism, built on motion, shaped by motion, and sustained by motion. Spin is not an optional feature. It is the mechanism through which nature transforms chaos into order. If rotation is both a product of cosmic imperfection and a necessary ingredient for structure, then the next logical question is how much of the universe's behavior can be traced back to this single physical property. To put it differently, if you removed spin from reality, would the universe even function? Or would it dissolve into something unrecognizable? Something that never forms stars or planets or atoms and eventually becomes a quiet, uniform fog of particles. This thought experiment is worth exploring because it highlights how deeply rotation is embedded in physical law. Imagine a universe in which every particle has exactly zero angular momentum at the beginning. No random bumps, no tiny motions, no slight twists, just perfect stillness. On paper, that sounds peaceful, maybe even elegant. But in physics, perfect symmetry is sterile. If nothing is moving, nothing will ever move. The universe, in this case, would be like a giant warehouse full of raw construction material that no one ever uses. There would be no gravitational fragmentation, because everything would be too perfectly balanced. Gravity needs microscopic irregularities in order to start creating macroscopic structure. Collapse requires unevenness. Once collapse begins, spin inevitably follows. Every time matter falls inward, it amplifies any trace of angular momentum because angular momentum is conserved. That conservation law is one of the most stubborn rules in nature. It refuses to let rotation disappear. Even when objects lose rotational energy through friction or radiation, that energy goes somewhere. It doesn't vanish, it moves. This is why collapsing molecular clouds turn into disks, not spheres. Why galaxies turn into spirals. Why stars flatten slightly at their equators. And why Earth is bulging at the middle, like someone who has been sitting too long during the holidays. It's also why we can say, with a straight scientific face, that rotation is responsible for the shape of almost everything you know. You don't normally think about planets as flattened spheres, because the effect isn't dramatic on Earth. But on Saturn, which spins rapidly and has less dense material, the equatorial bulge is unmistakable. Saturn looks like someone took a normal planet and pinched it. If you dropped Saturn into a lake, it would wobble like a water balloon. Of course, Saturn also wouldn't float because gravity is doing its thing, but the image is fun to keep. Stars flatten too, although we don't notice it easily because stars are bright balls of turbulent plasma with undefined surfaces. But rapid rotators, such as the star Altair, are noticeably oblate. The idea that stars should be perfect spheres is more of a poetic fantasy than a physical truth. Nature is a bad perfectionist. Rotation also influences temperature distribution. A rapidly rotating star tends to be cooler at the equator and hotter at the poles, due to a phenomenon called gravitational darkening. This is not a mysterious process, it's geometry. If the surface is farther from the center at the equator, it experiences slightly weaker gravity, which affects pressure, which affects temperature. Small differences amplify into measurable consequences. In a universe of motion, even subtle effects matter. The solar system offers additional drama. Many of the peculiarities that puzzled early astronomers, like why the planets orbit in a plane, why they rotate in similar directions, and why their moons generally fall into orderly patterns, are explained by rotational inheritance. Everything started in a disk. Everything inherited angular momentum from the same parent structure. That disk was chaotic, but the angular momentum was consistent enough to impose a general directionality. And yet, chaos found loopholes. Venus spins backward, Uranus is sideways, and Pluto is, well, difficult to categorize politely. These quirks aren't evidence that the universe made mistakes. They are evidence that early systems were violent and competitive. Young planets smashed into each other, merged, shattered, and occasionally got kicked out entirely. If you imagine the early solar system as a crowded dance floor where everyone is blindfolded, spinning wildly, and occasionally punching each other in the face, you're not far off. Spin influenced who survived. A planet that lost too much angular momentum might fall into the sun. A planet that gained too much might get thrown outward. A massive collision could redistribute angular momentum so dramatically that a stable orbit becomes unstable. Planetary systems aren't built like cars in a factory. They're assembled like sculptures made of spinning chainsaws. The Moon is one of the clearest examples of how spin and collision work together. The leading hypothesis is that a Mars-sized object, often called Theia, collided with the early Earth. The impact didn't just knock off a chunk, it melted both bodies, mixed their materials, and left behind a debris disk that eventually coalesced into the Moon. This event also sped up Earth's rotation and changed its axial tilt. In other words, Earth's 24-hour day, the existence of tides, and the long-term stabilization of Earth's climate may all be consequences of a catastrophic event that redistributed angular momentum. Rotation, therefore, plays a role in habitability, not metaphorically, but physically. A slowly rotating Earth might have weaker magnetic protection, a less dynamic ocean system, a different climate, and possibly poorer conditions for life. Too much rotation could have produced wild storms, unstable seasons, and so much equatorial bulging that the planet would resemble a fast-spinning blob rather than a familiar sphere. Habitability is not just about gravity, temperature, and chemistry. It is about motion. The ability of a planet to sustain life depends in part on how fast it spins and how its spin evolved. Stars face similar constraints. In their early stages, stars spin so rapidly that they can fling material outward. T-Tauri stars, which are young and temperamental, often eject mass through powerful outflows. Magnetic fields help remove angular momentum by transferring rotational energy into stellar winds. Without this process, stars could spin themselves apart. When astronomers talk about magnetic braking, it sounds like cosmic poetry, but it is literally the star putting the brakes on its own rotation so it doesn't explode. These processes don't just matter to academic theorists. They affect the disks around stars, where planets form. The material that gets stripped away might deprive future planets of mass, or it might deliver metal-rich dust into regions where rocky worlds can form. Angular momentum shapes the architecture of planetary systems just as much as gravity does. The reason our solar system is relatively orderly today is partly because spin was redistributed in ways that settled into equilibrium rather than perpetual chaos. Once stars mature, rotation continues to matter. Stars slow down over time because of magnetic braking, but the rate depends on mass, composition, and age. By studying stellar spin, astronomers have developed a method called gyrochronology, which estimates a star's age based on its rotation. Younger stars spin faster. Older stars spin slower. This is not guesswork. It is a measured statistical pattern. Spin becomes a cosmic clock. Rotation also influences explosive endings. When a massive star collapses into a neutron star, it does not lose angular momentum. It concentrates it. A neutron star can spin hundreds of times per second. The result is a pulsar, a magnetized, rotating object that beams radiation like a lighthouse. These beams sweep across space at almost unimaginable speeds, producing pulses that are so regular that pulsars rival atomic clocks in precision. They are the universe's metronomes, ticking away with relentless reliability. You could set your watch by them, assuming your watch could handle microsecond pulses from a stellar corpse. This becomes especially mind-bending when rotation couples with relativity. A spinning neutron star can exhibit frame-dragging effects, where the rotation influences space-time around it. Gravity is no longer just pulling, it is twisting. Light bends differently. Orbits shift. Even time itself is affected. Spin becomes a driver of general relativity in action. Not a theoretical abstraction, but a measurable, behaving feature. Black holes take this to an even more dramatic level. A non-rotating black hole is a theoretical object called a Schwarzschild black hole. A rotating one is called a Kerr black hole. The second type is the one nature actually produces. Kerr black holes are ring-like objects wrapped in distorted space-time, with ergospheres that drag anything within them along for the ride. This rotation can extract energy from infalling matter, producing jets that extend millions of light years. These jets, powered by spin, regulate star formation, heat intergalactic gas, and alter the evolution of galaxies. If you ever wondered how a tiny object can influence a structure thousands of times larger than itself, the answer is often rotation plus gravity plus extreme density. In this context, spin is not just motion, it is leverage. It is a tool that matter uses to manipulate its environment. The largest organized flows of energy in the universe, those enormous jets, are powered not by explosions, but by rotational extraction. It sounds counterintuitive, but most cosmic violence is rotational violence. Supernovae are just the fireworks preceding a lifetime of spinning drama. Rotation even shows up in gravitational waves. When two neutron stars or black holes merge, their spins affect the waveform, the oscillating ripples in space-time detected by observatories like LIGO and Virgo. The patterns in the waves reveal how fast the objects spun, and in what direction before they collided. We are not just seeing motion, we are reading motion encoded in the universe's fabric. Spin leaves fingerprints. On more ordinary scales, rotation influences climate, weather, and the physical behavior of atmospheres. Earth's Coriolis effect, produced by planetary rotation, drives global wind patterns and ocean currents. Without it, hurricanes would not form. Jet streams would not exist. Climate would be radically different. A non-rotating Earth wouldn't just lose its day-night cycle, it would lose the organized flow of heat. One side would face constant daylight, the other eternal night. Temperature gradients would become extreme. Water would freeze permanently in the dark and boil permanently in the light. The only habitable zone would be a narrow twilight ring circling the planet. The Earth we live on owes its livability to rotation, not just habitability zone placement. There is a strange irony here. Many people look at stars, galaxies, and planets and think of them as distant curiosities. But the same physical laws that govern their rotation govern the experience of wind, tides, and seasons. The spinning motion of Earth is not a background fact. It is a driver of biology, geology, and climate. You don't feel the spin directly, but everything you see is influenced by it. Scientists have even explored whether rotation affects geological processes. Earth's core rotates, convection occurs, and magnetic fields emerge from the dynamo effect. Without a spinning, molten core, Earth would lose its magnetic shield. Solar radiation would strip the atmosphere, boil oceans, and sterilize the surface. Mars is a case study in what happens when planetary rotation slows and core convection stops. Magnetic fields fade, atmospheres leak, climate collapses. It is reasonable to say that Earth's spin, inherited from a violent beginning, is a key reason you are able to read this sentence without needing protective shielding. Spin saves lives, silently, automatically, constantly. All these examples point to a conclusion that is easy to overlook. Spin is not an add-on. It is a structural principle. If angular momentum were not conserved, the universe would look fundamentally different. Matter would not collapse the same way. Stars might not form. Planets might not exist. Chemistry might not produce complex molecules. Biology might not arise. The universe's history, instead of being a long story of structure formation, might be a quick sigh of equilibrium. There is a lesson hidden here. Structure, complexity, and evolution often emerge not from perfect symmetry, but from the collapse of imperfect systems. A cloud of gas doesn't become a star because it was designed efficiently. It becomes a star because gravity drags it inward, amplifies its rotation, generates turbulence, heats it, and eventually ignites nuclear fusion. Spin is a sign that matter has fallen inward. Rotation is fossilized collapse. When you see a rotating galaxy, you are looking at the afterglow of ancient gravitational infall, still preserved in motion. Nothing in physics says rotation must stop. In fact, almost nothing can stop it. Friction slows rotation in small systems. Tidal forces slow the Earth's spin, but at large scales, space is too empty for friction to matter. Rotation becomes a form of immortality. Galaxies may one day stop forming stars, but their spin may persist long after their luminous matter has faded. The universe seems to favor motion. It is born in motion, evolves through motion, and leaves motion as a legacy. The idea of a static, motionless cosmos is neither stable nor natural. The universe is dynamic because physical laws push matter toward motion. And motion, when conserved, becomes rotation. From the smallest particles to the largest structures ever observed, spin is a recurring solution to a fundamental problem. How does matter store and organize energy while obeying the laws of nature? Angular momentum is nature's answer, and the universe is full of it. If spin is such a fundamental feature of matter and motion, it is natural to ask whether the universe itself is spinning. Not individual objects, but everything. Space, time, all of existence, rotating as a whole like a cosmic carousel. This idea isn't new. Philosophers wondered about it centuries ago. Early physicists considered it. Einstein flirted with it. Modern cosmologists still debate it. And, although it sounds like something you'd overhear at a dorm party at 3 a.m., it is a legitimate scientific question. There are two reasons this question matters. First, because a rotating universe would behave differently from a non-rotating one. Rotation would imprint measurable signatures on cosmic structure. Galaxies would align in preferred directions. Matter would flow unevenly, and there could be detectable twists in space-time. Second, because a rotating universe would change the interpretation of cosmic expansion. If everything is spinning, the expansion might not be uniform. Some regions might experience more acceleration than others. The geometry of the universe itself could be anisotropic, not the same in all directions. Modern cosmology assumes that, on the largest scales, the universe has no preferred direction. It is isotropic and homogeneous. This assumption is partly philosophical, partly observational, and partly practical. It makes the equations manageable. A universe that behaves the same in every direction is simpler to model. It is elegant, and science has a soft spot for elegant solutions, especially when they match data reasonably well. But over the last few decades, observations have questioned whether the universe is truly directionless. Galaxy surveys, starting with instruments like the Sloan Digital Sky Survey, revealed that galaxies are not evenly distributed. They form filaments, clusters, and voids, massive structures that resemble a cosmic web. This structure is not random, it has a pattern. Gravity, dark matter, and cosmic expansion shape it. Yet some surveys hint at large-scale alignment of galaxy spins, as if rotation on the level of galaxies is not entirely independent, but subtly coordinated. It would be misleading to say we have proof of cosmic rotation. We don't. But researchers are not ignoring the hints. They have asked whether the angular momentum of galaxies might emerge from initial conditions in the early universe. Perhaps turbulent motion seeded by inflation. Inflation, the rapid expansion that occurred fractions of a second after the Big Bang, could have created quantum fluctuations that, when stretched, became seeds for structure. Those fluctuations might not have been perfectly random. A tiny bias could have cascaded into observable correlations. Some scientists have proposed that large-scale rotation could stem from exotic physics, like torsion in space-time or cosmic defects left over from symmetry breaking in the early universe. These ideas are speculative, but they show that cosmology is not satisfied with simple answers. The standard model of cosmology works well for most observations, but that doesn't mean it explains everything. The universe may be orderly today, but its origins were chaotic. To understand why global rotation is hard to detect, imagine being inside a very large building that rotates extremely slowly. If the spin is gradual enough, and the building is big enough, you might not notice. The rotation would only reveal itself through subtle motions. Maybe objects drift slightly when left free, or long pendulums develop slight precession. In cosmology, this analogy plays out through measurements of cosmic microwave background radiation, galaxy orientation, and large-scale anisotropy. So far, the evidence leans toward a universe that is mostly uniform, but with tiny deviations that might represent rotation on scales we don't fully comprehend. Even if the universe is not rotating as a whole, rotation influences its expansion on smaller scales. Galaxy clusters experience frame dragging due to the motion of their components. On extreme scales, rotating supermassive black holes influence gas inflows, altering star formation rates. Rotation is not evenly distributed. It is localized, concentrated where mass accumulates. If the universe were truly static, with no rotation anywhere, gravity would crush everything into one point. The fact that collapse produces spin protects systems from total collapse. Angular momentum is a defense mechanism, a cosmic counterweight to gravity's obsession with compression. This dance between gravity and rotation also defines the behavior of galaxies. Galaxies don't just spin. They flatten because rotational support prevents collapse. Astronomers call this centrifugal balance, though the term is somewhat misleading because centrifugal force is not a fundamental force, but a consequence of inertia in rotating frames. Regardless of vocabulary, the outcome is consistent. Rotation gives galaxies their distinct shapes. Without it, galaxies would be lumpy balls, not elegant spirals and flattened ellipses. Real galaxies, though, are not simple disks. Their rotation curves, graphs showing orbital speed versus distance from the center, reveal surprising behavior. Stars far from the center of the galaxy move much faster than they should based on visible mass alone. The outer regions don't slow down as classical gravity predicts. This discovery, made in the 1970s by Vera Rubin and colleagues, changed astrophysics forever. It implied that there must be unseen mass exerting gravitational influence, a halo of invisible material that keeps stars from flying away. That material is what we now call dark matter. Rotational dynamics, not philosophical speculation, forced science to invent a new type of matter. That is how powerful rotation is. It exposes gaps in theory. When galaxies refuse to behave according to Newtonian expectations, the simplest explanation is that gravity is being applied by something we can't see. Dark matter, regardless of what it actually is, changes how galaxies spin. It keeps disks stable. It prevents fragmentation. It shapes the cosmic web. Without dark matter, galaxies might never have formed coherent rotating structures. The universe might be filled with diffuse gas clouds, not organized collections of stars. Rotation has therefore become a diagnostic tool for probing invisible physics. We can't see dark matter, but we can infer its distribution from how galaxies spin. The concept of using rotation to probe unseen physics extends to other domains. In neutron stars, spin rates and magnetic fields provide clues about internal composition. In accretion disks, rotational behavior helps estimate viscosity and mass transfer. In planets, rotational changes reveal interior dynamics. Saturn's rotation rate, for instance, has been notoriously difficult to measure because its atmosphere is chaotic. Scientists infer internal rotation by analyzing oscillations in the rings, waves caused by internal vibration modes. This method is arcane, but it shows how deeply interconnected rotation is with structure. Rings, moons, and atmospheres all react to internal spin. A planet is a system of coupled motions, not a rigid object. Rotation even influences how galaxies interact. When two galaxies merge, their angular momentum must be redistributed. gas clouds may lose energy through friction, allowing material to flow inward and feed central black holes. Stars, however, are collisionless. They often pass through unaffected. The result of a merger can be a distorted, chaotic system that eventually relaxes into a new shape. Elliptical galaxies, rounder, less structured than spirals, are often the product of repeated mergers that disrupted rotational order. Spirals are youthful, cold, and organized. Ellipticals are older, hotter, and disordered. Rotation is a signature of youth, structure, and dynamically cool systems. On smaller scales, the same principles apply. Planetary systems that form from disks may retain stable rotation for billions of years, as long as they avoid major disruptions. But gravitational interactions with passing stars can destabilize orbits. A single close encounter could eject planets, tilt axes, strip angular momentum, or trigger new rotation. This makes the universe inherently dynamic. Objects don't just spin, they evolve through motion. Spin is not a fixed quantity, it changes with time. Even Earth's rotation evolves. The Moon is gradually moving away due to tidal interactions, and Earth's rotation is slowing. Hundreds of millions of years ago, days were shorter, maybe 22 hours long. Coral fossils record this rhythm, preserving daily growth patterns that offer indirect evidence of historical rotation rates. In another 100 million years, days might stretch to 25 hours. Civilization will have collapsed or evolved beyond recognition long before then, but the planet will still be spinning, just slightly slower, like an aging dancer gradually losing speed. This slowdown is not trivial. If Earth slowed dramatically, perhaps through extreme tidal dissipation, its climate and habitability would change. Atmospheric circulation would shift. Seasonal patterns would stretch. Species that depend on circadian rhythm could struggle. Humans would complain about daylight savings on a planetary scale. Rotation is therefore not just a physical property, it is a biological factor. Life adapts to cycles. Planetary spin dictates those cycles. Remove it, and ecosystems collapse. Rotation also intersects with energy efficiency. The Earth's rotational kinetic energy is enormous, roughly 2.1 x and 10^29 joules. That's about 1,000,000 trillion times the total energy consumed by human civilization in a year. Yet, it is slowly leaking away into the oceans and the Moon because gravity is relentless. Eventually, if nothing else changes, Earth and Moon will become tidally locked, each showing the same face to the other, like dancers frozen in a mutual stare. At that point, days and months will be the same length. The system will reach minimal energy configuration, but this equilibrium lies billions of years in the future, long after oceans evaporate and Earth is a barren rock. Throughout cosmic history, rotation is a driver, a record keeper, a sculptor, and a constraint. It dictates how matter clumps, how energy flows, how systems evolve. If you asked the universe what its most persistent habit is, motion, specifically rotation, would be a strong contender. And beneath all of this is one simple truth. Angular momentum is conserved. That isn't just a rule. It is the way reality stores information about motion. When objects collapse, they spin. When objects collide, they exchange spin. When systems lose energy, they shed angular momentum in some form. Radiation, jets, mass loss. The universe is full of mechanisms that redistribute energy, but it has very few that erase it. There is a deep philosophical comfort in this. Systems change, but their motion echoes through time. The spin of galaxies today is a remnant of processes that began billions of years ago. The spin of Earth is a fossil of catastrophe. The spin of atoms is a manifestation of quantum rules older than stars. Motion is memory. The universe remembers through rotation. If angular momentum is such a powerful conserved quantity, then any event that significantly redistributes mass must also redistribute spin. This principle drives some of the most dramatic phenomena in the universe, particularly the formation of compact objects like white dwarfs, neutron stars, and black holes. These objects are the corpses of stars, not metaphorically, but literally. They are the leftover cores of stars that have exhausted their nuclear fuel. And, like any collapsing system, they spin faster as they shrink. It may sound strange to describe a star as shrinking, because stars are enormous, colossal pressure vessels where nuclear fusion pushes outward against gravity. But eventually, fusion stalls. The outward pressure fails. Gravity wins. The star collapses in on itself. If the star is sufficiently massive, this collapse is catastrophic. The radius shrinks by a factor of thousands or millions. And since angular momentum must be conserved, spin increases to compensate. The same principle explains why figure skaters spin faster when they pull their arms inward. Their moment of inertia decreases, so their rotation rate increases. But cosmic skaters operate at absurd scales. A collapsing stellar core can rotate hundreds of times per second. That corresponds to surface speeds approaching significant fractions of the speed of light. Neutron stars, in particular, are famous for this. They are formed when the core of a massive star collapses so violently that protons and electrons combine into neutrons. The resulting object has the mass of the Sun, but only about a 10-mile radius. Imagine stuffing an entire mountain range into a teaspoon and spinning it faster than anything you can imagine. That's a neutron star. These stars are not just spinning lumps. They have magnetic fields, and not normal magnetic fields, but monstrous ones, trillions of times stronger than Earth's. When a rapidly rotating object with a strong magnetic field exists, it tends to emit beams of electromagnetic radiation. If those beams sweep past Earth, we see pulses. That is why neutron stars are called pulsars. They blink rhythmically, like cosmic lighthouses, and they don't blink out of laziness or whim. They blink because their rotation and geometry force beams to sweep through space at predictable intervals. These pulses are astonishingly regular. Some pulsars are more stable than atomic clocks. They spin tens, hundreds, even thousands of times per second. The fastest known pulsar rotates 716 times per second, about once every 1.4 milliseconds. You cannot blink that fast. Your brain cannot process events at that frequency. Yet a dead star can. Even black holes, which are often misdescribed as simple objects with no structure, possess spin. When matter collapses into a black hole, its angular momentum cannot simply vanish. So, black holes typically rotate. A rotating black hole drags space-time around with it. A phenomenon called frame dragging, predicted by general relativity. In extreme cases, this dragging can accelerate particles to ultra-high energies or twist magnetic fields into jets that blast material out at nearly light speed. We now know that most galaxies, including ours, have supermassive black holes at their centers. These black holes often spin rapidly because they were fed by rotating accretion disks. and accretion disks themselves rotate because angular momentum prevents matter from falling straight in. In fact, one of the most counterintuitive aspects of cosmic rotation is that it prevents gravity from doing what gravity really wants to do: crush things instantly. Instead, matter must lose angular momentum in order to fall inward. This requirement forces accretion to be messy, inefficient, and spectacular. That inefficiency creates some of the brightest objects in the cosmos. Quasars, which are powered by supermassive black holes devouring matter, can outshine entire galaxies. They radiate because matter in the disk rubs against itself, heats up, and releases energy before being swallowed. The same physics applies to smaller systems: protoplanetary disks, X-ray binaries, and even the rings of Saturn. Rotation traps matter in a waiting room where it must shed angular momentum before it can enter the main chamber. This waiting room model also explains why galaxies generally form disks. The collapse of gas into stars is hindered by angular momentum. It is easier for gravity to collapse a system vertically than radially. That's why disks are thin but wide. Stars form in the disk, not in the halo, because the halo is not rotationally supported. Angular momentum sculpts shape. The thinness of the Milky Way's disk is not an aesthetic choice, it's an equilibrium condition. There is a poetic irony in this, though we promised not to be too poetic. Gravity and rotation constantly argue about geometry. Gravity wants spheres. Rotation wants disks. The final structure depends on who wins. On small scales, gravity dominates. Planets and stars become spheres. On larger scales, rotation wins. Galaxies spread into pancakes with spiral arms. If you could compress the Milky Way into a solid object you could hold, it would look more like a compact frisbee than a ball. Spin also explains why planets have atmospheres. Rapid rotation generates circulation patterns, storms, and jet streams. If Earth spun significantly faster, weather would be more extreme. If it spun slower, weather would be sluggish and perhaps less supportive of life. Jupiter's rapid rotation, a 10-hour day despite its enormous size, produces violent storms and striped cloud bands that circle the planet indefinitely. Saturn's hexagon-shaped polar storm might also be linked to rotational dynamics, though the precise mechanism remains debated. Rotation fosters complexity in fluids. That complexity influences climate, and climate influences biology. The fact that Earth rotates at a moderate rate, not too fast, not too slow, plays a quiet but non-trivial role in habitability. Faster rotation might have shredded early life with constant megastorms. Slower rotation might have produced global stagnation. With feeble winds and minimal nutrient circulation in oceans. This is speculative, but emerging research in paleoclimatology supports the idea that Earth's rotation rate subtly shaped its evolutionary history. Even the length of a day mattered biologically. Early cyanobacteria experienced shorter days, with different sunlight cycles. Their circadian rhythms adapted. Whether rotation influenced early evolutionary pathways is unclear, but it is increasingly obvious that daily periodicity is baked into the molecular machinery of life. Clock genes exist in nearly all organisms. These genes regulate behavior, metabolism, and cell division. Living systems internalize rotation. They entrain to cycles imposed by planetary spin. If the planet had different spin characteristics, life might have evolved differently. Rotation also affects orbital stability. Without spin, Planets might not maintain axial tilt. Without tilt, seasons wouldn't exist. Some organisms rely on seasonal cycles to reproduce, migrate, or survive harsh conditions. All of these processes trace back to the fact that Earth rotates, stabilizes, and wobbles just enough to produce rhythmic variation. It is not oversimplification to say that rotation makes life dynamic. If you remove spin from the universe, you still have matter, but you lose much of the structure. Stars would collapse faster. Disks would not form. Galaxies would not organize. Atmospheres would stagnate. Weather would disappear. Oceans would not circulate. Climate would freeze into monotony. Life would be constrained to small, static environments, if it emerged at all. A world without spin is a world without movement, physically, biologically, and perhaps intellectually. Rotation is not just a curious byproduct of physics, it is a central organizing principle of cosmic structure. It emerges automatically because of conservation laws. It shapes matter because of geometry. And it persists because nothing exists to erase it. Physicists study how rotation influences cosmic evolution using simulations. These computational models incorporate gravity, fluid dynamics, magnetic fields, and sometimes radiation. They track the evolution of matter from the early universe to the present. Simulations reveal something remarkable. Rotation emerges naturally, even from random initial conditions. In chaotic systems, angular momentum becomes distributed throughout structures. Tiny fluctuations amplify. Large-scale coherence arises spontaneously. The universe doesn't need a cosmic hand to set things spinning. Spin is a mathematical inevitability. This self-organizing principle appears even in laboratory experiments. When physicists cool clouds of ultra-cold atoms to extremely low temperatures and perturb them, vortices often form. Miniature whirlpools in quantum fluids. These vortices are quantized, meaning they can only have discrete values of angular momentum. You cannot have half a vortex, you must have a whole one. This constraint hints at deep connections between quantum mechanics and macroscopic behavior. Quantum mechanics, in fact, treats angular momentum differently than classical physics. Electrons possess intrinsic spin, but that spin is not literal rotation. It is a mathematical property related to symmetry. Yet this abstract spin manifests in real effects: magnetism, chemical bonding, spectroscopy. The entire periodic table is shaped by spin properties of electrons. If electrons did not have spin, chemistry would look nothing like it does. Life almost certainly would not exist. This leads to a strange but profound observation. Spin is woven into reality from the smallest scales to the largest. Elementary particles have spin. Atoms have spin. Molecules have spin. Planets and stars have spin. Galaxies have spin. It is hard to find anything that doesn't possess angular momentum. But why is that true? Conservation explains persistence, but not origin. There is a deeper question. Why did the universe form rotational motion to begin with? If everything started from a symmetric, uniform state, shouldn't motion cancel out? One hypothesis is that the early universe was never perfectly symmetric. Quantum fluctuations, predicted by inflation theory, guarantee randomness. If you roll a ball down a perfectly symmetrical hill, it could go anywhere. But in practice, it will choose a direction, because microscopic imperfections break symmetry. The same principle could apply cosmologically. Another hypothesis is that rotation is simply the most natural way for matter to exist under gravity. In any collapse process, tiny deviations from symmetry get amplified. Rotation is an attractor state, the endpoint toward which chaotic motion tends. The universe gravitates towards spin because spin stabilizes structure. This spontaneous emergence of order from disorder is not unique to cosmology. It appears in meteorology, oceanography, plasma physics, and even traffic modeling. Systems with flows and constraints often self-organize into rotating structures. Hurricanes, cyclones, Jupiter's storms all emerge from energy gradients and angular momentum conservation. If you could step outside the universe and nudge it, you might see similar structures everywhere. Rotation is also deeply tied to curvature. In Einstein's relativity, mass and energy determine how space-time curves. Rotation modifies this curvature further, twisting the geometry. Rotating objects do not just warp space, they drag it along. This effect has been measured near Earth using satellites like Gravity Probe B. The twist is tiny, but real. On cosmic scales, frame dragging could influence accretion flows, jet formation, and high-energy phenomena. These interactions between rotation, gravity, and curvature are central to modern astrophysics. They show that angular momentum is not a trivial secondary property. It is a key player in shaping cosmic evolution. Matter does not fall, it spirals. Space does not stretch uniformly, it swirls. Energy does not flow linearly, it circulates. It may sound anthropomorphic to say that the universe likes rotation, but mathematically, it behaves as if rotation is favorable. Alone, gravity creates a collapse. Rotation preserves structure. Together, they create complexity. This raises an interesting speculative question. If rotation is so fundamental, is it possible that consciousness, life, and complexity ultimately trace back to the physical consequences of angular momentum? That is, did the universe spin itself into a state compatible with complexity, rather than stagnating in collapse or chaos? It's a playful idea, but not entirely absurd. Complexity requires gradients, circulation, feedback loops, and persistent structures. Rotation creates all of those. In a static universe, complexity would struggle to emerge because systems would not sustain dynamic equilibrium. Evolution, biological, chemical, or cosmic, depends on time, variation, and structure. Rotation creates them. Of course, this is more philosophical than empirical, but sometimes philosophy helps illuminate scientific questions. Even if life itself is unrelated to cosmic spin, life depends on the environment created by spin. The cycles, the flows, the stabilization of planetary climates, the formation of galaxies. We exist because the universe moves. When scientists try to describe why rotation is universal, they often fall back on mathematics rather than metaphor. That is reasonable. Equations describe how angular momentum emerges and evolves. But beneath those equations is a deeper narrative. Not mystical, but structural. Rotation is what happens when matter behaves under gravity in a universe with conservation laws. It is less a why in a moral sense, and more a why in a functional sense. The universe rotates because rotation is the equilibrium state of motion. If this sounds anticlimactic, remember that science often replaces mystery with mechanism. But mechanism can be beautiful in its own way. Not because it makes the universe simple, but because it reveals the architecture behind complexity. Without rotation, the cosmos would be simpler, quieter, and dramatically less interesting. Stars would die faster. Galaxies would not form disks. Black holes would not produce jets. Weather would vanish. Days and nights would lose meaning. Life might never emerge. Spin is not just a detail. It is a backbone. The universe is dynamic, and rotation is its most persistent gesture. If rotation is so fundamental to cosmic architecture, then one might wonder whether it has always existed or whether it emerged during some transitional period in the early universe. The short answer is that angular momentum didn't suddenly appear. It developed as matter evolved under gravity, but its roots trace back to the earliest instance after the Big Bang. The universe itself was not born spinning like a giant cosmic roulette wheel. Instead, it began as a hot, dense, rapidly expanding field of energy with minute fluctuations imprinted by quantum processes. Those tiny irregularities became the seeds of structure, and as matter condensed, it spontaneously developed rotational motion. This makes rotation less of a cosmic preference and more of a mathematical inevitability. When matter collapses under gravity, it rarely falls perfectly symmetrically. Even microscopic imbalances result in torque, and torque leads to rotation. The same principle applies when a cloud of gas collapses into a protostar. An imperfect shape plus gravitational contraction equals spin. The universe is messy, and that messiness gets amplified. That amplification becomes structure. So, while we often marvel at spiral galaxies, pulsing neutron stars, and elegantly rotating planets, these outcomes are not miracles. They're what happens when physics takes random starting conditions and forces them into stable configurations through conservation laws. In cosmology, this process is often studied using large-scale simulations. These simulations take simple initial conditions, slightly denser regions embedded in a mostly uniform early universe, and evolve them forward using laws of gravity, hydrodynamics, and thermodynamics. What emerges is stunning: filaments of galaxies, rotational flow patterns, clustering, and networks of mass that span hundreds of millions of light years. Researchers call these structures the cosmic web, and importantly, this web is not static. It displays circulation patterns, vortices, and directional flows. The universe doesn't just expand, it also swirls. Rotation appears at multiple scales simultaneously. Inside galaxies, stars orbit the center because of gravitational attraction combined with angular momentum. Dark matter halos, which envelop galaxies and provide most of their mass, also possess rotational characteristics, though their motion is more chaotic and diffuse. On grand scales, clusters of galaxies show rotational features, though less organized than individual galaxies. There is no single cosmic axis, no preferred direction. Instead, there are countless small whirlpools embedded within larger whirlpools, nested like Russian dolls. Some researchers have wondered whether the entire observable universe rotates in a subtle way. This would be mind-blowing, because it would imply that space-time as a whole possesses angular momentum. Observational data so far suggests no global rotation, at least not within measurable limits, but the question continues to attract interest because a rotating universe would produce detectable signatures, such as frame dragging on massive scales or anisotropies in cosmic background radiation. The current consensus is that if any cosmic rotation exists, it must be extremely weak. But whether or not the universe spins as a whole, almost everything inside it clearly does. Even the most stable systems experience rotational evolution. Earth's rotation, for instance, is slowing by about 1.7 milliseconds per century due to tidal interactions with the Moon. The Moon itself is receding from Earth by about 1.5 inches per year. Billions of years from now, Earth might be tidally locked, always showing one face to the Moon, just as the Moon currently always shows one face to us. Tidal locking is not an exotic phenomenon. It is a natural endpoint for many rotating systems. Mercury is partially tidally locked to the Sun in a 3.2 orbital spin resonance. Many Jupiter and Saturn moons are fully locked. Tidal locking occurs because systems dissipate energy over time, but they must preserve angular momentum. The result is synchronized rotation, like dance partners who eventually fall into step. On even longer scales, galaxies will also evolve. Stars gradually lose angular momentum through interactions, radiation, and mass loss. Galaxies collide, merge, and their rotation gets redistributed. These mergers can erase spiral structures and create elliptical galaxies, which are less rotationally supported. In this sense, galaxies have life cycles. Spirals are youthful, energetic, and dynamic. Ellipticals are older, more relaxed, and more chaotic internally. Their stars move in random directions, like a crowd at a shopping mall rather than cars on a racetrack. Even here, angular momentum doesn't disappear. It gets diffused. Rotation and decay operate in parallel. Systems spin, redistribute, and settle, but only to the extent that physics allows. Some rotations are practically immortal. Pulsars, for example, will continue spinning for billions of years, gradually slowing but never stopping entirely. Black hole spin may persist until the heat death of the universe. Even an isolated black hole loose in mass through Hawking radiation would retain angular momentum until its final quantum moments. If the universe ever ends in a cold, empty state, it may still contain rotating objects, lingering like ghostly relics of motion in a mostly motionless cosmos. Angular momentum is not just an attribute of matter. It is also a source of energy. Many astrophysical processes extract energy from rotation. Black hole jets, for example, are partially powered by rotational energy extracted via magnetic fields. The Penrose process, a theoretical mechanism, suggests that objects entering a rotating black hole's ergosphere can escape with more energy than they entered with, effectively tapping into black hole spin like a cosmic power generator. While we cannot engineer such processes, nature does it effortlessly, producing jets that shoot across thousands of light years, seeding interstellar space with heavy elements and shaping galactic evolution. This connection between rotation and energy has profound implications for cosmic evolution. Without rotational energy, many of the universe's most luminous phenomena would not exist. Gamma-ray bursts, some of the most violent explosions ever recorded, are linked to rapidly rotating collapsing stars. Accretion disks radiate because of friction between orbiting material. Planetary magnetic fields, which protect atmospheres from being stripped away, are powered by rotating cores. In a very practical sense, spin sustains environments, powers mechanisms, and maintains diversity in cosmic structures. If the question, why does the universe spin, is framed narrowly, the answer is simple: because angular momentum is conserved and asymmetry exists. But if the question is framed broadly, What role does spin play in the evolution of complexity? The answer becomes deeper. Rotation delays collapse, prevents stagnation, and enables systems to remain in dynamic equilibrium long enough for structure and diversity to emerge. Without spin, everything might fall straight inward, accelerating cosmic death. Earth, for example, is not merely a rock spinning in space. Its rotation creates cycles, day and night, that regulate temperature, weather, and ecosystems. Wind patterns distribute nutrients, clouds move water, and oceans circulate heat. Life evolved in response to these rhythms. Circadian clocks, found in cells from bacteria to humans, are biological reflections of planetary spin. Without rotation, Earth would have no day-night cycle, no seasons, and no stable atmospheric circulation. Life might still exist, but its form, complexity, and evolutionary path would be entirely different. When people ask existential questions about the universe, they often focus on extreme concepts: black holes, dark matter, multiverses. They rarely ask why motion exists. Yet motion, not matter, is what keeps the universe from collapsing into triviality. Spin is not an ornament, it is a scaffold. This leads to an interesting scientific observation often understated in textbooks. Most complex systems are metastable. They are not in perfect equilibrium. They are balancing forces, losing energy slowly, but trapped in long-lived states. Rotation is a mechanism that creates metastability. It provides a buffer between collapse and dispersal. It allows matter to linger in interesting configurations. Galaxies are metastable. Stars are metastable. Planetary atmospheres are metastable. Even life is metastable, balanced between entropy and order. And rotation is a key ingredient in this delicate balance. The universe is not static, because static systems are short-lived. It is full of movement, because movement extends lifespan. If there is a poetic conclusion to draw, without being overly poetic, it's that motion is not a defect of the universe. It is its engine. The cosmos did not wind up and then slowly unwind like a clock created by a watchmaker. Rather, motion is emergent, self-reinforcing, and fundamental. It is not imposed, it is derived. We live in a universe that is constantly negotiating with its own rules, preserving what cannot be lost and rearranging what can. The reason everything spins is not that the universe is whimsical. It is that physics forbids stillness in any evolving system. Angular momentum is the bookkeeping of motion. It records every interaction, every asymmetry, every collapse, and refuses to let anything go unaccounted for. In that sense, the universe is obsessive. It will allow matter to change form, but not to forget its history. This is why, when we look up at the night sky, we see spiral galaxies, rotating stars, orbiting planets, and clouds of gas swirling in gravitational wells. We are witnessing an accounting system older than atoms, one that emerged before there were even structures to spin. Spin is a fossil of imperfection. It is also a mechanism of endurance. If you want to summarize the entire story in one sentence, it could be this: the universe spins because rotation prevents collapse and enables complexity. It does not spin for mystery, or for beauty, or for meaning. But meaning emerges anyway, because a universe in motion makes room for evolution, diversity, and curiosity. Our ability to ask why the universe spins is, in a small way, an outcome of rotation itself.